Good evening, folks, and welcome to the stream. We have just about 5 minutes to go until tonight's puzzles unlock. That's day 23 of Advent of Code. As always, I'm going to be working through solutions in C++. If you have any questions, feel free to drop those in the chat, and I'll do my best to answer them on the stream here. Or if you're watching the replay later on YouTube, you can feel free to leave a comment, and I'll try and answer you in the comments. As always, the code that I write you can find up in my GitHub repository. That's at github.com/Craig-Chasseur/AOC2020. You can see it on the screen right there. Also, you can find the link to the GitHub repository down in the description there. And you can find stream replays on my YouTube channel, youtube.com/spoonboy42. And, of course, there's always the live streams on Twitch. No matter where you're seeing this, just check the description for links. So, we are getting close to the end of this year's Advent of Code. Only 3 more nights of puzzles left, which is always a little bittersweet, but you know, we've had a lot of fun doing it this year. I hope you've had fun with me doing this. Last night, we played a little game of what the puzzle called Combat, what you might also recognize as the card game of War. And we had a special recursive version that we had to implement, playing against the crab on our raft as we're finally sailing to our tropical island vacation. You know, I think the last couple of nights have been a little bit easier, especially compared to, like, say, day 20, which was the one where we had to kind of assemble that jigsaw puzzle from the Elf spy satellite to find the sea monsters. And looking at the stats here, that has still the fewest full solutions. But I actually really liked that puzzle once. I mean, I was frustrated with it first on the night of and didn't get a solution right away, but once I got some sleep and came back to it, I wound up really liking that puzzle and the way that each part of it kind of built on the last part of it and came together into the overall solution. So we'll see. I don't know. You know, maybe we'll get another pretty difficult one tonight, or maybe we'll get another one that's, you know, kind of medium like the last couple of nights have been. We'll see. But of course, you know, it's different for everybody. Like, I think a lot of people thought day 19s with the recursive expression parsing was really difficult, but I actually didn't find that too hard. But, you know, I found the Chinese remainder theorem one to be really difficult. So, you know, everybody approaches these problems differently and has a different experience with them. So in the last couple of minutes before tonight's puzzle unlocks, let's go ahead and just get a head start by doing what we do every night and making a new directory for tonight's puzzles. And we'll make just a minimal C++ program for our Part 1 solution. You've seen me write this same code many times if you've been following the stream. And we'll make the build file so that the Basil build system that we're using knows how to build it. Yeah. And we'll go ahead and build and run that just to make sure that everything is working as it should. Okay. We are good to go. We might as well, since we have a little bit more time, I'm just going to include the check and I/O libraries that I wrote we've wound up using on most days just to do file I/O and to do assertions. And we'll put the dependencies in for that as well, because most days we wind up needing those. We might as well put those in ahead of time. Go ahead, compile and run again. Okay. So we have just about 10 seconds left until tonight's puzzle unlocks, as we continue sailing on our raft towards that tropical island. All right. Small crab challenges you to a game. Oh my goodness, our crab friend is challenging us. Okay, so cups will be arranged in a circle and labeled clockwise. Okay. Before the crab starts, it will designate the first cup in your list as the current cup. The crab is then going to do 100 moves. Each move, the crab does the following actions. The crab picks up the three cups that are immediately clockwise of the current cup. They are removed from the circle. Okay. Interesting. So we have kind of a circular structure here. We take stuff in and out of and rotate around. Okay. That just gives us our puzzle input right there. All right. Okay. So we may not actually need our I/O library because we've just got our hard-coded puzzle input from the first one. But let's write a class that represents the state of the cups. So we'll just call that class cups. And we have various choices for representing kind of this circular thing of cups. We could, actually make it a circular linked list. I think I'm just going to use a deck, and we can make it so that, like, say the first item in the deck is the current cup. I mean, I may change my mind about this, but that's what I'm feeling like doing right now. And so we'll just have integers for the actual cups in there. We'll have a constructor where we can initialize the cups, let's say from a span. Okay. So see, now that I see that we're removing stuff and putting them back, I actually kind of think that a list might be the most efficient way to do this now. Yeah. A deck is fine. Like, shuffling this stuff around in memory, I'm not actually that concerned about. So this move method, we'll say that the first the first element in the deck. Oh, I'm sorry. I haven't actually been showing you my code this whole time. Well, now you can see where we're at. Sorry, I meant to show you this. We've got this cups class. We initialize it with a list of cups. And now we're just getting ready to implement the crab's moves. So we'll say that the first element of cups is the quote-unquote current cup. And then we remove the three cups to that are immediately clockwise of the current cup. So we'll say that, the circle goes around clockwise. So we'll just use the standard array class because it's going to be fixed size. Going to be cups.begin plus 1. So the cup immediately after the front cup, and then cups.begin plus 4 because we want 3 past that for the removed cups. Why is this? Not letting me initialize this from iterators. Well, maybe I don't want to do it in an array if it's not going to let me do that. I'll just use a vector. All right, so we've got the removed cups. Now let's actually erase them. We will say so we erase that range from cups. So now we select the destination cup. So that is the cup with a label equal to the current cup's label minus 1. If at any point in this process the value goes below the lowest value on any cup's label, it wraps around to the highest value on any cup's label instead. So that is going to be not counting the ones that are currently in the list. So what we will do is we will search for the highest label below the current cup's label, and also just the highest label, the highest value on any cup's label overall. And if the current cup is the highest one, I think it could actually be the current cup itself. But yeah, we'll go ahead and do that. So we'll say we'll use iterators to refer to these. So we'll run this. So we'll just go through all the elements in cups and find the highest one that is below the current cup's label. If that one if such one exists, we'll use that. Otherwise, we'll wrap around. So if we haven't already found that, or the new version is lower than what we've already found for highest below current, we will replace highest below current with that value of the iterator, with that iterator. Otherwise, if the highest overall it hasn't been set, or sorry, that should be if the iterator is greater than highest below current, because we're trying to find the highest one that still meets this condition. Yes. Or the overall. Now for this one, if we haven't set the highest overall, or this value is greater than what we have already found for the highest overall, we will replace highest overall. When both of those should now be not at the end. And highest below current doesn't necessarily have to, that doesn't necessarily have to be, I realize now, doesn't necessarily have to exist. Because we could have wrapped around to do highest overall. So say if highest below current is not the end, we will use highest below current. Otherwise, we have to use highest overall. So next thing we do is we place the pieces that the crab just that the crab picked up, so that they're immediately clockwise of the destination cup. So to do that, we'll do cups.insert from that destination position plus 1, so immediately after that destination position, and then we are going to put in the cups that we removed at the beginning. Suppose this can be const, come to think of it. Again, dec isn't necessarily the best choice here because we're going to have to copy some stuff around, but like these arrays are small. I'm not particularly worried about whether dec or list is going to be more efficient here. But then the crab selects a new current cup, the cup which is immediately clockwise of the current cup. So in this case, that just means we cycle around the front to the back. So So I think that implements the crab's moves. And then we just have to do this. A 100 times. Okay. So, well, and then we actually have to produce the string. So, the really cool thing is that I think absol stir join will do this for us. right. We'll just hard code the input in here, I guess. So the test input from the puzzle is that, but with individual digits. So and then my actual puzzle input I will put in here as well. So then first we'll do it with the test input as we usually do. Run it 100 times. Spit out that order string. And I think this is the solution. So we just need strings and span from abseil. We actually do not need that IO library. Let's go ahead and run it. So that gives us the order after cup 1 would be 6, 7. Okay. Oh, okay. We have to start after the cup labeled 1. I see. Each number except 1 should appear exactly once. I mean, we can kind of just hack it right now, and I promise I will fix this, but just for the sake of expediency, like, we can fix that string ourselves. We can cheat a little bit and just fix that as humans rather than, running that the actual way it's supposed to be. Okay, so we have 1 here. We'll say 825 followed by 73496. Let's see if that is correct. All right. Ooh, we did really well on the leaderboard, too. Okay, part 2. Due to what you can only assume is a mistranslation, you're not exactly fluent in crab. You are quite surprised when the crab starts arranging many cups in a circle on your raft. 1 million in total. Your labeling is still correct for the first few cups. After that, the remaining cups are just numbered in an increasing fashion, starting from the number after the highest number on your list and proceeding one by one until 1 million is reached. Okay. And the crab is going to do 10 million moves. Crab is going to hide your stars, 1 each, under the 2 cups that will end up immediately clockwise of cup 1. You can have them if you predict what the labels on those cups will be when the crab is finished. Oh my gosh. Okay. So, 1 million cups and 10 million moves is probably going to be a little bit much to brute force, I think. So we might need to figure out a way to do this a little better. Or maybe not. I mean, like, we could genuinely try and brute force it, but I don't know about that one, folks. Let's go ahead and copy our day 1 solution, our part 1 solution rather, to part 2. Yeah, this is where I begin to think that maybe, worrying about the efficiency of some of these data structures might come into play. Although, I don't know. If we just tried to adapt our solution here, I wonder what we would get. Not going to need stir join to produce that result anymore, but we'll say so. You want find, pretty sure, yeah, from the algorithm library. If 1 happens to be at the actual end of the sequence, we just have to wrap around. You just do that twice for each of the 2 entries after number 1. And then return the product. It's going to be 9 elements, yeah. Filling the whole thing up to 1,000,000. Taking about 4 megabytes of memory to represent this whole thing. Oh man, the copying around is going to be bad. Oh, maybe I do want to do a linked list. I don't know. We'll see. But I it might not even just be the efficiency of the data structure. It might be that, we just have to do something algorithmically more sophisticated. And I'm not really sure of that yet. But I want to just try brute forcing it and see what happens. See how far we can get. And it's the 10 million moves that kind of kills me here, but we'll see. And I just want to see, how fast we move through this. So we'll say just if and, Just 3 Fs. Just give ourselves a little progress indication to see how it's going. All right. So we've got our brute force method here. Copy part 1 to part 2 in the build file here, and we will see how far this gets us. Taking a pretty long time. Let's try it a little more frequent logging. Even more frequent than that. Okay, so you can see this is going to take quite a while to get up to 10 million. So we definitely need to do better. There are ways that we can make this brute force solution more effective by lessening the amount of memory copying we need to do around by using a linked list rather than a deck. But I kind of think that is missing the point a little bit, and we maybe need to just think about how to make this algorithmically better, like figure out a non-brute force solution, a non-brute force approach to this. Although, maybe just for my own edification, maybe I will convert this to a linked list. Okay. Yeah, I mean, let's go ahead and do that for now. No longer going to need a deck. Yeah, it's not going to let us add directly. Yep. Okay. Write a little helper here. So you can't just like add directly an integer onto a lists iterator, because the list iterator is not random access. You always have to like go one step at a time, but since we're only going up to 3 steps, not so bad. Oh, and I meant to put them up here, of course. So the one advantage of list is that provides us this splice method that we can transfer elements between lists and preserve their pointers to each other. Like, it's a more efficient way of splicing subranges that linked lists afford us. So and then we can splice them right back. We can do the whole removed cups list there. And then this rotation from front to back is really the same. Although it will allocate more memory, so maybe we want to I wonder if we can splice the thing itself, like if that's allowed. Yeah. We'll see how much faster it gets with just this optimization. Like, I would hope that we see it start to go faster with the list than the deck, but it's still not going to be that fast. Yeah, like, you can't really tell that it's all that much faster. Okay. So, just using a data structure, which one would hope would be more efficient for this, still isn't that great. So let's try and think about the problem. Try and think about this in a more sophisticated way. So you pick up 3 cups that are immediately clockwise. We look for a cup with a label equal to the current cup's label minus 1. Okay. I mean, one way, again, to make this brute force algorithm a little bit a little bit more efficient is that if we actually hit the current label -1, we can just terminate early. Um, Go ahead and break that whole loop. But again, this is still kind of just fiddling with the brute force solution. But yeah. Man, this crab has a lot of cups. Okay, thinking a little bit about this. So now I'm thinking about again, I don't have a huge algorithmic insight here, but I realize that we could do a lookup table such that because these iterators in the list have iterator stability. That is something afforded to us by using standard list. We could make this search for the next number a lot more efficient by using by making some kind of a lookup table for it. So I think I'm maybe going to try that. Again, using quite a lot of memory for all this, but I want it. What can I say? I want to do it. Why would it need to provide a call operator? Oh, flat hash. Sorry, flat hash map, not flat hash set, obviously. Okay. Okay. Now let's make a little helper method to find the destination. So first thing we'll do is we will subtract, we'll decrement that current value, and okay, so that shouldn't be const, but we'll pass in the current value, we'll decrement it to find the value that is one less that we're looking for. If that goes down to 0, though, then we are going to want to reset current value to the max number, which is, 1 million. Then if the value that we're looking for is in removed cups, we don't want to use it because it's not actually in the circle that we're dealing with at the moment. So if it's in that, we will just continue on to the next iteration of the loop. But otherwise, we should be able to find the destination in our lookup table. So we'll say auto it goes lookup table dot find current value. You'll check that that's not the end of the lookup table. We'll return that iterator to the destination. Okay, so now this whole thing where we find the destination iterator, we use that helper method, find destination. We splice in those removed cups, and then we just need to update the iterator pointing to current then when we pop from the front and push on the back here. So lookup table, and I hope that the iterators that have been to the elements that have been spliced through these remain valid. I'm not 100% sure about that iterator stability guarantee, but I really hope that it holds. We'll see, though. If not, we will have to do a little more bookkeeping in lookup table. But that's, you know, not the worst thing in the world to do that additional bookkeeping. I should probably figure that out, though. But anyway, so we decrement that before using that. That should give us the right iterator. So if find destination is much closer to being constant time now than being linear time in the size of the list, let's see how fast we go. Okay. Oh, we need to include flat hash map, obviously. Okay. Time-space trade-off strikes again. We are blasting through moves now. I mean, it takes a few seconds, but we get somewhere. And that is the right answer according to the website. Let's do it with our actual puzzle input. Oh, I am psyched about this. Thank you, Lookup Table. Spend more memory, get faster. All right, let's see if this is correct. Could be real psyched if it is. All right! And rank 251, that is maybe my best so far this year, I want to say. Let's look at personal leaderboard here. I believe, yeah, 251, the best we've done this year. I have to believe, you know, this took a few seconds. This took a little while to run, but still finished in reasonable time. Like, we still had to run 10 million iterations of the simulation, but the thing that really saved us was that each iteration of this game did not take a ridiculously long amount of time. In particular, we didn't get up to this situation where we had to search through all million elements of the ring in order to find the destination, because we had that hash-based lookup table. So we could do actually, looking up in the lookup table is a constant time operation. We might have to do up to 3 or 4 lookups in the table because things can be in the set of removed things, but there's still, a low upper bound, so it is for all intents and purposes constant time. So, even having to really run the game for 10 million steps, we still finished in a reasonable amount of time and got the correct answer. Thanks to the time-space trade-off, that we got from having this lookup table of knowing exactly where every numbered cup is. So, I have to imagine that there is probably something that is maybe even more algorithmically clever, that you maybe don't need to simulate all 10 million steps of the game, but we managed to get there by just making the simulation of each of those steps more efficient. If the parameters of the puzzle were such that you had to simulate the game for 1 billion steps, then maybe we'd start to sweat a little. But yeah, we managed to get there. So I also think that it was probably the right idea to switch from a deck to a list as well, because although a list can be fragmented in memory, a linked list, each individual node is allocated separately. It definitely uses more memory. The indirection can be inefficient in certain ways. The ability for us to splice things in and out easily without having to copy half of the underlying storage probably made a big difference too. So choosing the right data, I guess the moral of the story partly here is that choosing the right data structures makes a big difference for efficiency. And even though most of the time in C++ you can just say, use a vector, it'll be fine, don't worry about it. This is one case where, when you have to insert or remove things in the middle of a sequence, avoiding copies by being able to just splice the nodes in directly, which you can do with a linked list, helps with the efficiency. But then the other part of the secret sauce is for sure this lookup table. And another thing that makes this lookup table possible, though, that we can get to the iterator, get to the position in the list, and not just a value there, is that a linked list has pointer stability for its values. So when you allocate a node of a linked list, no matter if you insert stuff in front or behind it, the actual position in memory, the address of that node, is going to be the same. And going up a level of abstraction in the C++ standard library, those iterators in the linked list are going to remain stable. And it seems like they even remain stable if you splice stuff from one list into another list. So those iterators act like pointers to the nodes in the lists, and as long as those nodes still exist, as long as those values still exist in some list, those iterators still point to quote-unquote the right thing. So we can store a bunch of them in this lookup table and not worry about them getting invalidated when we are splicing every which way here. So I think I'm about ready to call it a night. Getting that solution in there. Like I said, 251 is definitely a personal best on the leaderboards this year. I'm very happy with that. Like I said, I do suspect that there is probably something even more sophisticated here that you can do that doesn't actually require you to simulate 10 million moves of the game. But we made it fast enough that it's practical. So this is, brute force plus. It's not fully brute force. We made the algorithm a little bit smarter using a lookup table, which is kind of a time-space trade-off. But this is smart force. So I thank you all for watching the stream again. As always, the code will go up in my GitHub repository. That's github.com/Craig-Chasseur/AOC2020. Stream replays will always be on my YouTube channel at youtube.com/spoonboy42. No matter where you're watching this, you can find all those links down in the description. We've got 2 more nights of Advent of Code. I really look forward to going through those puzzles with you. and finally reaching our well-deserved tropical vacation. Good night, everybody.